So, and high momentum jets have a large momentum, so it's logical that when you look at collisions with mini jets or very big jet, very hard jet, that you should see a rise in the average momentum. But now, when you look at this in P-LED, you see that it's changed a little bit, not very much, but you still see this kind of a same rise. And so you can still, it's not clear what's going on, but then you shift into lead-lead, now as a function of collision multiplicity from peripheral to central, and you see again the same phenomenon, but obviously the slopes are very, very different. And so given that I showed you a moment ago that there's a lot of attenuation at large momentum, meaning that jets are suppressed or jets are at the very least interacting with the opaque medium, it means that what we see here is no longer the simple jets, if they were, it's no longer the simple jets that were seen in PP. There's something new here. And so some people try to analyze this in a simple-minded way by doing what's known as a blast wave fit. And so in a blast wave fit, there's an expression here encapsulating what the blast wave does, but the concept of a blast wave is illustrated here. You have the participant region. The participant region is expanding under pressure, under the pressure gradient. And so it means that a given cell of fuel, not fuel, but of QGP is being accelerated by the pressure. And so picture that this cell of fluid is now being pushed radially out. And so the particles that are produced in that cell are going to be Lorentz boosted radially. And if you think about this, if you're on the periphery of the nucleus, or not the nucleus, but the fireball, if you are in the periphery, there's no pressure from outside, it's vacuum, but there's a lot of pressure from inside. If you're smack in the middle, straight in the middle, there's equal pressure from all sides. And so the gradient of pressure in the center is vanishing. The gradient of pressure on the edge is the largest. So you have a trend that rises with the radius of the fireball to produce larger and larger gradient of pressure or applied force on the cell or the particles within the cell. And so the notion then is that the velocity, the transverse velocity of the particles in the cell becomes proportional to some power of the radius of the cell, normalized, mathematically normalized to some maximum radius. And so you can do the calculation assuming that within the cell particles are produced isotropically, and then they are boosted isotropically and thermally. So at given zero chemical potential but a finite temperature. And so you take this Maxwell-Boseman expression, and then you boost it, and you get this formula. The formula itself is not that important unless you do the actual calculation. What's important is the result, is that we can get from this kind of fit, we can get an idea of what is the boost undergone by the particle as well as the temperature they reach in the cell where they're produced. And so this graph here illustrates this.
This depends on a measurable parameter, which is the radius, the distance of the cell to the center, right?
Yeah.
Which you cannot measure.
You cannot.
That to the data.
Right. So this is you have to average over all of this. You play with the exponent. You fit the data.
Of exponent and the radius.
Yep. Yeah, and then you hope you get, yeah, I mean, there is obviously a model. And you can ask yourself how good is the fit? And the fits are actually quite reasonable. And so what you get out of this is a so-called kinetic temperature as a function of the average transverse velocity. And you see that in this context, PP collisions and lead-lead collisions behave very differently. What do I have? PP? The purple point are at the top here, and so for different classes of collisions, you seem to have the same temperature but different velocities. Whereas for lead-lead collisions in red, you find that as you go towards more central collision, you have larger velocity but smaller temperature. So it's as if as the system expands, it's going faster and faster in more central collision, but it's expanding until it cools down to smaller temperature. Similar results were obtained by other collaborations. Now the blast wave model is a very simplistic model, of course, and so there are calculations done in hydrodynamics by hydrodynamic models. And the upshot is that here you have pion, kaon, and proton pp bar spectra, and they are pretty well reproduced by the calculations. So this gives us some confidence that at the very least in lead-lead collision, there's some kind of a fluid that is produced. This fluid is undergoing large pressure gradients and is expanding really, really fast. And I really want to emphasize fast. Here we are at 0.7 of the speed of light, 70% of the speed of light. So, and that's the average. So this matter is exploding at extremely high velocity. You can look at many other things here. For lead-lead and PP collisions is a ratio of d bar to deuteron. And what is fascinating is that the ratio is shown in different centrality classes. The ratio is always 1. As a function of PT, the ratio is always 1. And so what that tells us is that it's equally likely to make an antiparticle than it is to make a particle. Now in PP collisions, you don't see this, but you do see that in lead-lead, and that tells us that somehow when you make this, the fireball now is made of, consists of quarks and antiquarks, and there's enough quark and antiquark to randomly form antiproton protons, anti-deuterons, and so on and so forth. The same results have been obtained for PP bar, DD bar, T bar T, and so on. So it's quite spectacular, in fact. It tells us that really we seem to have deconfined the quarks, and they can rearrange themselves into making any other type of particle. And we can study this, in fact, quite quantitatively based on a thermodynamic model. And so this has been done now as an industry, in fact, by our colleagues, in particular at GSI and Heidelberg. And so you posit that you can describe the system in terms of a grand canonical system or grand canonical ensemble. This is the partition function of that system. And from there you can calculate the densities of each of the species. So you plug in the mass of all the particles that you produce. You account for decays of resonances that are heavy into these ground states, so to speak. And so here are the production yield in the acceptance of the TPC. And we compare data from Alice and results from these statistical or thermal model. And so obviously there's a fit involved here. You have some parameters. There are chemical potentials. There's a temperature. The temperature is assumed to be the same for all particles. It is assumed to be the same throughout the system. And with such simplified model, this is what we get. And so you have, for different particle species, pions, kaons, phi, pp bar, lambda, all the way to helium bar, strange helium, where you take one neutron and you replace it by a lambda or an anti-lambda. And so even there, you see that the points, the data points from Alice compared to the statistical model are in exceedingly good agreement. So what this tells us is that whatever this thing is that we form in lead-lead collision, it does behave very much like a thermal system. Now you can ask, how good is the fit? The data over fit ratio is shown here for all the species, and one can argue that it's actually quite good. The only perhaps strong discrepancy that there is in explaining the yield of pp bar. There seems to be some issue here, but people are working on this. So with this, I hope that I was able to paint a picture of a system that is thermal, equilibrated, and exploding violently. And so that's the understanding that we have, I think, based on these quote-unquote simple observables. Now we can go into the business of measuring correlations. So for the next few minutes, I will try to do that. And so one of a large body of works has been done in the business of what's known as flow. And so this schematically illustrates what you have when two nuclei collide. One nucleus comes in the page, the other goes out of the page, and you have an overlap region shown in purple. The purpose of this slide is to illustrate that the overlapping region is not a smooth and perfect region. It can fluctuate. But this region then has a shape. This shape can be characterized by ellipticity, or you can characterize the shape by moments of the shape in coordinate space, second order, third, fourth order moments. And as I've argued already several times, the fact that this shape is anisotropic means that there is a gradient of pressure which is different along the different axes of this shape. So in the case of an elliptical shape, you have smaller distance along this axis, so that will lead to larger gradient along this axis. So you expect particles to be emitted along this axis. But you can also have assembly of particles that look like a triangle. And if you do, then you should have a radial push that might have the shape of a triangle. And so this, of course, would amount to a fluctuation associated with the initial conditions of the system. It's not something that you would see on average. On average, you would see something that is perfectly elliptic and perfectly symmetric. But in collision by collision, you can see such fluctuations. So we are detecting particles relative to some reference azimuth, and then we try to understand how we can Fourier decompose this production, the anisotropy that we measure. And we characterize this by a Fourier decomposition as shown here, where the coefficients, the first few coefficients are given a name of directed flow, elliptic flow, triangular flow, and so on. What is to be understood here is that at very low momentum, where the speed of the particle is modest relative to the expansion of the system, the velocity of the expansion of the system, the pressure will have time to act on the particles and then actually push them. And so the particle spectrum will react to this push. And so the pressure plays a role very much at low momenta. At high momenta, particles are essentially moving at the speed of light. They go through the system before the system has really time to react very much. So what matters at very high momentum is how thick the system is in any given direction. And so if you have a particle going along the long axis or along the short axis, they will experience different amounts of energy loss. So at high momentum, one expects and what I would, or the so-called hard sector, one expect path length dependence or suppression associated with the orientation relative to the reaction plane, whereas at low momenta, one expects the role of pressure, that the system behaves more like a fluid. And so just to illustrate what I'm saying is that given different second, third, and fourth order spatial anisotropy, when you form this Quark-Gluon plasma, it will expand and perhaps keep some memory of the initial spatial anisotropy. And it does. So this is shown, this is a result that was obtained in 0 to 1% collisions lead-lead by Alice. This is a correlator, like the one I've talked about yesterday. Slightly different normalization, but be it that is the same idea. And so the measurement is shown in blue. The fit, the red line is a fit. And what you'll notice is the existence of this dip on the away side. To explain this dip, one needs a strong E3, a strong triangular component, and only with the existence of this triangular component that you can explain this strong dip. There was a lot of work being done in 2005, 2010 to try to understand this, whether this could have been due to some Mach cone effect, but it turns out that it's flow. So here is the result that was originally obtained in 2001 by the Star collaboration. This is V2 plotted as a function of the relative multiplicity relative to some maximum. And as such, it's not telling you much, but it is compared here to calculation that, well, state of the art at the time, ideal hydrodynamic calculation in the rectangle. And what you find is that at least for this region of centrality, collision centralities, there's a very good agreement, in fact, between the calculation and the data. And this led to the notion of, okay, we made a perfect fluid. Why? Because we are able to reproduce the data pretty well with ideal hydrodynamics. Ideal hydrodynamic means no friction, no viscosity. And so this was also studied, of course, in 2010 by the Alice collaboration. This is V2 measured by Alice with different types of methods shown in red and blue are Star results, and in the dots are Alice results obtained by different techniques. This is the so-called event plane technique, two particles being correlated. And the red points are the so-called 4-particle cumulant technique. And the idea is that with a 4-particle cumulant, you are suppressing effects associated with V2 fluctuations. And I'll come back to that in a moment. And so we were able to show our V2 maps as a function of square root of S. And we see that it seems to be rising. Now, the fact that it was rising was at first somewhat of a puzzle, because if you think in terms of the system being opaque and having some gradient of pressure, the initial thoughts were that this would level off. What we find here is that the V2 is increasing because the average PT is increasing with square root of S. Now, I said perfect fluid. It's clear that the fit or the comparison of the spectra I showed you was not perfect. Comparison such as this one were done with Star results, Phoenix results, and eventually with Alice and CMS results. It became abundantly clear that ideal hydrodynamic was good, but not perfect. So the fluid is not actually perfect, and so it became clear that perhaps we can understand one of the properties of this fluid, that is, we can understand or can measure the viscosity of of this fluid. And so a lot of people are involved in this literally industry of trying to understand the viscosity of the Quark-Gluon plasma. And so this is a simulation by Bjorn-Schenker where you see initial conditions, you see the system after 6 Fermi/c of evolution without friction, without viscosity, and then you see the same system but after 6 Fermi/c but with viscous hydro, and you can see that here it's very spotty, it's very granular, there's a lot of granularity, but you find that this granularity has been smeared out by viscosity. That's what viscosity does. And so can we really understand this? Well, again, just to emphasize the role of shear viscosity, if you have a fluid, if you have laminar flow, as illustrated here, and thanks to my friend Alex, if you have cells of flow that are or laminar flow that are moving at different velocities, if there is no friction between those cells, they will continue their merry way without slowing down or accelerating. But if you have viscosity between inside the fluid, the fast lane will slow down and the slow lane will speed up, and so you'll have equilibration. And so that's what you would have with laminar flow along one axis. If you have this now in azimuth, it means that in practice, if you had a lot of V2, a lot of anisotropy, by having large friction, large viscosity, you would damp, you would reduce, suppress this V2. And that's what is shown here. V2 is shown as a function of the PT of the particle. This is a calculation with different values of viscosity. And so essentially no viscosity, some 0.08 in some units, and a lot of viscosity. You can see that the presence of viscosity can very much affect the magnitude of the V2. And this was done also for species, but that's technical details that we can skip through. Before I go too far along this direction, I want to emphasize that there were a lot of tests to understand all the details, the technical details that are involved here. One such technical detail is the possibility that there is, well, we're measuring a correlation. When you measure correlation, it doesn't tell you what the cause of the correlation is. So what we are of course thinking is, well, this correlation, this anisotropy that we see is due to this hydrodynamic flow or some differential attenuation. But really, could there be other phenomena at play here? And of course, one such phenomena would be the presence of jets or mini jets. Jets have an orientation in space, and so if you take these particles and you calculate their average, their V2, you will see some finite results. So what people did then was to study the flow coefficient V2, V3, V4 as a function of a rapidity gap. That is, you look not only at particles that are close to one another in phase space, but very far apart in phase space. And by doing that, you're able to suppress the role of jets. So if you have particles that are within a jet, they will all go in the same direction. That will contribute to cosine 2 phi, cosine 3 phi in the same way. If you put a rapidity gap between the particle, you will suppress the contribution of those jets. And so people then started looking at correlation at long range with small and large rapidity gaps. People did this now not only with 2 particle correlation, but also 4 particle correlations. So here I have 4 from the 4 particle cumulant that I talked about yesterday, 6 particle cumulant, 8 particle cumulant, and skipping the details, you can show that if you really have true flow and true correlation to the reaction plane, then the flow coefficient is the fourth root of this coefficient, 6th root and 8th root. Now, needless to say that these measurements require extremely good precision in understanding of the detector. So what we see then is that now we can take these correlators, so this is C24, C26, 6 particle, C28, measured as a function of the particle multiplicity, and we map them by these formula onto this graph. And so this is V2 now as a function of the multiplicity, and what you find is that these coefficients map onto essentially a universal curve. And when we do this, we can do this with rapidity gaps, no rapidity gaps, and we get the same result. So that tells us that when you eliminate non-flow effects and when you eliminate flow fluctuation, you have a beautiful consistency between all these correlators, and that tells us that there's really a long-range collectivity in lead-lead collisions. And we can try to apply the same trick in smaller systems, of course. And so, having accomplished this, now we can focus on trying to really understand the system and some of the properties of the system. And so this is a simulation, this is a comparison of calculation by Charles Gale and collaborators. Vn as a function of the centrality, so V2, V3, V4, V5, and so we don't have data on this plot for V5, but hard to measure, but we have a good comparison for 2, 3, and 4, and we compare with the model, and in this case the model has an eta over S, or shear viscosity per unit of entropy, of 0.2. And so we see that with this much viscosity, we can in fact obtain a very good agreement with the data. Now, truth be told, you can change the viscosity a little bit down, a little bit up. You still get a good agreement, and there are obviously many technical issues that I'm not an expert at, and so I will not attempt to discuss, but there are many ways to increase the viscosity or decrease the velocity, changing the initial condition and so on and so forth, such that you get pretty good agreement with the result. But I think the point is that we are now at a level where the precision of the data is such that we can have very good conversation with the theoreticians and understand some of the properties of the Quark-Gluon cloud, namely the viscosity. This is yet another type of results or thing that people have looked at, so-called symmetric cumulant, which I'm not going to try to explain, but again, there's a comparison with models, and the models are actually comparing very well with the data. If you're interested in subtleties, I'm going to show just briefly. This is V2 as a function of centrality at 2.7 and 5.2, obtained with 2 particle correlations and 4, 6, and 8 particle correlation. And so, and that you see in each case 2 sets of curves. The higher curve is obtained at 5.02 TeV, the lower is at 2.76, and you have obviously 2 sets here. And so there's a big gap or big difference between the 2 sets, and what we've done is to be able to, and I'm not going to be able to really pay justice to the argument, but we have convinced ourselves that this gap is associated with flow fluctuations. Because flow fluctuations are really suppressed when you look at V4, V6, and V8. Now, what is spectacular about this is you now can take ratio of V6 to V4, V8 to V4. That's what's shown here in these 2 colors. And you can see that V6 to V4 and V8 to V4 are mapping on a universal curve, which is not 1, which has some dependence on centrality, which tells us that the fluctuations are not Gaussian. If the fluctuations were Gaussian, this would be unity. But it tells us that we have some very high precision in trying to understand theoretically what's going on here will be very interesting. Theoretically, people have compared the 2 energies, and you can find that the ratio of the flow coefficients measured at the 2 energies for V2, V3, and V4, these coefficients are reproduced very well with a modest amount of viscosity. So we are, I think, in very good shape to understand the equation of state, at least as far as the viscosity is concerned. And these results were also these considerations were also done for xenon. So I'm showing here the red points are xenon for V2, black points for V3, and compared to the results in lead. So we see that there's a slight difference in xenons. What's interesting is when you take the ratio of xenon to lead, you find that in peripheral collision, the coefficients are smaller than, the ratio is smaller than 1, but when you get to the most central collision, the ratio is larger than 1. And what's interesting here is that we know from other consideration that xenon is a deformed nucleus, and we see this deformation right here. Other consideration that are of interest is looking at the momentum dependence of flow, and I'm not going to spend a whole lot of time on this, but this now has been done with a very large momentum range. This is showing from 1 GeV essentially to 14 GeV rather, and for different particle species. And what's of interest here is to note that there is a gradation or a hierarchy or an ordering in the momenta at low, the V2 at low momenta. And so because we have a fluid and the fluid expanding at a finite velocity, the fluid velocity drives the momentum of the particle. And so at equal V2, you will have different momenta for these different particles. And you will see that as you increase the mass of the particle, you shift to the right. And so that's this ordering in momentum that is expected, indeed, if you have a fireball that expands. But there's, obviously, this is the low momentum regime. There's a more complicated regime where this phenomenon is not happening. What instead you find is that you have two sets of curves. You have essentially two universal curves, so to speak, one associated with baryon, one associated with meson. And this tells us that the nature of the particle, whether they contain 2 quarks or 3 quarks, probably has something to do with the amount of flow that we have. So if you have quarks, if you have 2 quarks that are flowing at the velocity of the medium and they bind, they will have a momentum which will be larger if they are baryons. So at equal V2, you would shift to the right. And of course, there's a third region where this effect seemed to be going away, and now you're in the what I would call the damping or the attenuation or suppression region. And so there doesn't seem to be much of a difference between baryon and mesons. Let me skip ahead. I want to show some of the results, some of the stuff we did at Wayne State, briefly. And how much time do I have? Okay. So with my previous postdoc, Prabhat Pujahari, we got interested in measuring not only number correlations, but momentum correlations. Momentum correlation is is essentially what Victor measures for his thesis, but with a slightly different definition of the correlator. The correlator that we used here is it's a dimensionless correlator, so we measure this so-called delta PT correlator, and we normalize it or divide by the square of the average PT of the particles, so that makes it dimensionless. And so this correlator is essentially related to the density of the 2 particles with a weight corresponding to the deviation from the average mean of the momentum of the particles, so-called delta P, delta P, delta P being the difference of a particle momentum to the mean. And we showed in a paper that delta PT is actually sensitive to collective anisotropy or transverse anisotropy, and we were able to extract some relationship between the flow coefficient or the harmonic coefficient of number correlation and P2 correlation. So there's a very simple pocket formula that one has that relates the two coefficients. And so what we did here is to measure both of these correlators and see what they look like. So what we have, starting with the number correlator R2 is, this is in central collision, the delta eta axis, delta phi axis. This is the near side. This is the away side. So this is what you have in central collision, peripheral collision. So you see, what do you see here? You see in delta phi, you see a very strong modulation corresponding to flow. You see a near side peak. And, oh, sorry, this is 0 to 5. This is all 0 to 5. Now, what am I talking about? I don't have perf. I don't. This is like sign on like sign. I apologize. So this is charge independent. So the point is that we have a very strong peak here, and we have strong modulation. But what we did with this comparison is to look at P2 in most central and R2 in most central, and what you find is this very sharp modulation, and it's specifically this dip on the away side. If you recall what I showed you a few minutes ago as a projection in delta phi, I showed you that when there's a dip on the away side, that corresponds to the presence, strong presence of a third harmonic. Well, these are the same collisions, right? So what we find is that P2 is more sensitive to the presence of the third harmonic than R2 is. The next thing that we did is to compare these two, and what do I have here? We have the data itself, which is in blue, the solid symbols, and we have this formula that I just mentioned a moment ago that translate harmonic coefficient measured in R2 into harmonic coefficient that would be expected in P2. And what we find is that if you go to large rapidity gap, 0.9 to 1.9, there's a very good agreement between the prediction, quote unquote, and the measurement. And so that tells us that at large rapidity gap, flow actually dominates. Correlation to the reaction plane actually dominate. It should not have been any surprise. In fact, it wasn't a surprise, but it was neat to be able to verify the presence of or the existence of flow dominance in these correlation functions as well. We can, of course, try to look at a small system and find out whether there's flow there. I apologize. This looks like not very good quality slide. And so, is there a flow in small system? Let's skip this then. So, is there collectivity in PP or P-LED? So this is a very busy plot. I apologize. This is Vn for two particle in for several particles here. This is V4, V6, V24, V26, V22, V32, V42. So there's a lot of results here. And it's shown as a function of multiplicity from 0 to central collisions lead-lead. And the message of this slide is to see that in lead-lead, you have this enormous amount of flow, V2, finite V3 and V4. But in PP and P-lead, in this region, you have a small amount, but not zero. So, and you can do this with or without rapidity gap, with sub-event methods where you try to decorrelate and get rid of these non-flow effects. The story remains that there is evidence of some collectivity here. What is the nature or the origin of this collectivity is unclear. So that's an open story, although I was on a court matter, maybe people have better answers today. I want to emphasize briefly, but the full story will be told tomorrow by Victor, that we've spent quite a bit of time trying to understand the viscosity of the QGP from another perspective, that of measuring momentum correlators. So these are very beautiful results that were presented by Victor at Quark Matter in 2017 in Venice. And so you see this correlator G2 that is shown here, and he will talk about it in great detail tomorrow, so I will not steal his show. But so you have flow modulation, and then you have a peak on the near side, and the peak is changing shape, is broadening with centrality, and there's a prediction by our colleague Sean Gavin and others that the broadening of this peak tells us about the viscosity of the system. Victor will talk about that tomorrow. I want to spend 10 minutes, if I have time, to speak about my last love, so to speak. And that's the story of balance function. Balance functions were proposed by Scott Pratt and collaborators already in 2000, so that's 19 years ago. The idea of balance function was that they should enable us to understand the evolution of the system that we produce in either gold-gold or lead-lead collisions. So the picture that these guys came up with is as follows. And so this plots the number of quarks, but you also could plot the number of gluons as a function of time, the time elapsed through a collision. And so you have crossing of the nuclei here, and as the nuclei cross, you have immediately quark-quark, gluon-gluon interactions, and so you start immediately making some quarks, U bar S quarks. You also make a lot of gluons. In fact, you make mostly gluons. And so I'm not plotting it here, but the number of gluons shoots up, and you have dominance of gluons. And so now for a short amount of time, you have a bubble of Quark-Gluon plasma, at least in this picture, that is going to expand longitudinally because the gradient of pressure is maximum along, you have two pancakes, right? And so the pressure gradient is maximum along this axis. And so this system is going to expand this way at nearly the speed of light, and then it's going to expand a little bit transversely at not quite the speed of light. While the system expands, it's not emitting particles very much, so the idea is that you have isentropic, or expansion of the system without too much of a change in entropy of the system. Eventually the system becomes dilute. The quarks and gluons have to combine to form hadrons. The hadrons themselves become dilute. The system freezes out, or it falls apart, and it decays. But before it falls apart, you have to transform all these gluons into quarks first, and then combine those quarks to make hadrons. So the notion that was in vogue then is that you have isentropic expansion, and at the very end, when the system is about ready to fall apart, then you have hadronization, and you produce a lot of pions, shown in green, and a modest amount of strange kaons or other types of strange particle. So the idea is that you have strange, the fabrication or the synthesis of strange quarks and UD quarks at the beginning and at the end. So you have a two-phase production of quark. Now, up and down quarks are very light, and so when the temperature is low, it's relatively easy to make up and down quarks and the hadron that you can combine them into. But strange quarks are heavy, and so it's more difficult to make them when the temperature is small, easier to make them when the temperature is high. So the relative number of strange to up-down quark should be larger initially than at the end. So that means that whatever correlation exists between particles that you make, if they involve a strange quark, this correlation has a lot of time to expand as the system expands. And so Pratt and Company predicted some correlator that they called it G, the name is not so relevant, as a function of the rapidity distance between the particle. And they predicted that pions and kaons would have different correlator shapes, and the shape would depend on whether you have initial emission or final stage emission. So they argued that if we measure this type of correlation between correlated particles, charge-conserving particles, we would be able to see the difference between this stage and that stage. And so this became a quest to measure balance function. So I will explain in a moment technically what a balance function does, but essentially you measure, let's say you measure a plus particle, a pi plus. By virtue of charge conservation, there has to be a minus somewhere. The question is, where is the minus? And so in Pratt's mind, if the pair is produced very early, the distance in rapidity between the plus and the minus will become very large because they have a lot of time to go away from one another. If the two particles are emitted very late, they don't have a whole lot of time to move away from one another, so they will be closer in rapidity space. And so if you think in terms of correlation function then as a function of the rapidity difference between two particles, if the emission is early, you should have a broad correlation shown in black, pp. If you have late emission or a larger fraction of late emission, you should have a narrow correlation shown in blue. So the idea was then to look for such a narrowing of the correlation function. Now, such a narrowing of the correlation function is to be expected if you have preponderance of pion emission and not a whole lot of strangeness emission. But so this narrowing was expected for pions. But since one expects a fairly modest amount of strangeness production in the late stage, one would expect that the kaon balance function would not be very much modified with collision centrality. There are, of course, as usual, all kinds of technical subtleties, but here is the expression of the balance function. It's not pretty. But the idea is that you look at correlation, two-particle correlation, plus minus. You normalize by, let's say, the plus. And so you count how many particles are associated, or how many negative particles are associated with a plus particle. And then you subtract how many plus particle are associated with a plus particle so that you can get rid of trivial effects associated with energy conservation and so on. And then you have minus and plus and minus and minus. So that's the nature of the beast. And technically the way we measured this was by means of so-called R2 correlators, and this illustrates how the measurement goes. You start with unlike sign, plus minus, and that's the kind of correlator that we see as a function of delta y, delta phi. This is the kind of correlator that you see in like sign pairs, and so so you see this flow modulation that is very strong. You see a near side peak, nothing on the away side, something similar here. But when you subtract the two, you end up with something that looks like this. You end up with, again, delta y, delta phi. You end up with a peak. The peak has a certain width. There's also a hole in the middle. The hole comes from the fact that we're looking at pions. Pions have an HBT, and HBT wants to, produces a very narrow peak. This very, very narrow peak here is pion condensation, and so the hole, so you're subtracting a big peak, so that makes a big hole. So that's this hole is then associated with HBT. But the idea is that you have this beautiful peak here, and we're going to look at how this peak is changing with centrality. So we just to illustrate how this goes. We have unlike sign, like sign, and then the subtraction. This is for central, mid-central, and peripheral. And so focus on the bottom. You have the balance function in central to peripheral. So what you can see for pions is that there's a clear change in the shape and width of the balance function from peripheral to central. And that's exactly what we expected from Pratt's argument that there should be a narrowing due to late hadronization. I cheated a little bit, however, and I did not talk about this here. Remember, I spoke about the blast wave model, and I told you that in the blast wave model we have emission from a source. The source is a certain radius. The radius, the cell is moving at some velocity, and so this cell moving at a high velocity, all the particles emitted in the cell are going to be kinematically focused. And so what this kinematical focus does is to narrow the balance function. And so a big fraction of the narrowing that we see here, sorry, not this one, a sizable fraction of the narrowing that we see here is, must be in fact due to this collective flow. Anyway, just to get to the punchline, PhD student Jin Jin, who worked with me for many years and is very familiar with the group here, produced this fantastic set of balance functions. So you looked at pion pairs, pi k, pi p, k pi, k k, k p, pi p, k. So these are the balance function that you got as a function of centrality. Obviously, too small to be really understood here. Let me focus just on pi pi and kk. And so again, I've shown this already. You can see from peripheral to the right to central to the left that there's a narrowing of the pion balance function. What is now interesting is that in the case of the kaon, we have now no evidence for a strong narrowing of the balance function. And so this is in line with the argument of Pratt that kaons might have been formed early, and consequently, if they're formed early, they would expand far in rapidity, relative rapidity, and there would be no contribution or very little contribution from the late stage. And so consequently, when you average and you integrate everything out, that you would see no change with centrality.
How many chaos are there in the peripheral events?
Oh.
2 chaos maybe?
No. In this rapidity range, centrality is 70-80. You can get a handful of kaons, and in the most central you get very many.
But how does it play the role here? For example, the rho or the phi. The rho will decay very quickly, and the phi may. So what happens to you?
Yeah. So very good.
Sorry,
No. You don't be sorry. That's a very good question, and it's a big concern. In fact, it's not totally resolved, to be honest. Obviously, the phi decays into k plus, k minus, and so you can have a contribution of the phi in this peak. The phi is pushed out, radially out, so it will decay in this peak. What we've estimated is the phi contributes some large fraction to this, 30, 50%. But we need to do a little more work to quantify the contribution of the phi. And there's a possibility that we can actually eliminate the phi and have an answer without the phi. But we haven't completed that yet.
Mainly because the question was mainly because the decay, the lifetime of the phi is very different from the rho, for example.
The lifetime of the phi is larger than the lifetime of the Quark-Gluon plasma.
So could it be that it goes away from
when
you decay, you don't know?
Well, there's a possibility. I mean, there's a possibility that the phi could be suppressed because it's destroyed, but the phi, I've never seen this argument. The argument that I've seen is that the mass of the phi would be shifted.
No, but I meant. You will decay.
Or the width of the phi would be shifted. So but we never saw the mass shift really, but we saw some suggestion that the width could be changing, which would be either because the mass has shifted a little bit or because the actual width has changed. But no, but this is a very, very, very valid question, and I can't give you a straight answer yet. And so if you're interested, we can look at this as projection onto the delta y-axis. It's easier to see how things are changing. So again, pi pi, pi k, pi p, and so on. And so you can see that the pi pi is changing a lot. Much of this change, of course, is due to HBT. Pi k is also changing, but here there's no HBT. PP is not changing a lot. What's a little frustrating with PP is that we only measure a small fraction of the balance function of the PP. Obviously, there's something happening on the outside here that we can't measure. And so, so let me translate this into the width of these balance function obtained by Jin. So this is the longitudinal width in rapidity, in azimuth, and then we can also take integral of these balance function and see how they evolve with centrality. So the blue curve is the width of the pion, so we see the pions are narrowing. Part of it is the HBT effect, but part of it is also radial flow, obviously, and there can be two-stage hadronization. The kaons, KK, are in the stars, the red stars, so they're not changing, but the argument that you just articulated with the phi is a problem. And then the others are all narrowing a little bit. And so, and they narrow, so the story here is that the kaon is not narrowing in longitudinally, but it is in fact narrowing azimutally. And the narrowing azimutally is expected whether you have a phi or not. You have to have this kinematic focusing in phi, not necessarily in eta. So we see here a lot of narrowing in phi with collisions, increased collision centrality. But the story is more complicated longitudinally. I was hoping that we would have some insight and some easy answer in trying to interpret these results without models. At the end of the day, there are too many parameters, too many things to consider. So we are awaiting smart theoreticians to help us make sense of all of this, because there are a lot of, unfortunately, there's a lot of physical effects. As I said, radial flow, the presence of resonances, and delayed hadronization or two-stage hadronization. But to really understand everything will take very detailed model capable of describing all these phases. So, I know for a fact there are some people interested in this and already looking at this. 5 more minutes? I wanted to also speak about something that was essentially invented in Alice by my colleague Voloshin, who has invented many other things. And it has to do with event shape engineering. Event shape engineering is interesting because it enables us to study different types of phenomena by trying to control them. So the idea is that at LHC energy, and to a lesser extent at star energy or RIC energy, there are so many particles that are produced that you can event by event or collision by collision have an idea of the shape of the event. And in other words, you can estimate event by event what is the amount of V2 or V3 in the event. And so how do you do this event by event? So you build a so-called flow vector. The flow vector is, you have Qx and Qy. You're summing for each of the particles within an event the sine and the cosine of their angle multiplied by n being the order of the flow vector that you're interested in. So typically n equal 2 or n equal 3. And then you normalize by the multiplicity. So this is so-called the flow vector. And this flow vector now in this simulation is plotted on the vertical axis as a function of the V2 that is put in event by event. And so this was an actual simulation done to demonstrate that you could actually, event by event, understand the amount of flow that is produced in the collisions. And so this is Q2, and you can see that it's very well correlated with the V2 that is plugged in the simulation. So by changing the V2 that you plug in, you see that you can you have a different value of Q2. So that tells us that by measuring Q2, we can control the shape, or approximately the shape of the event. Okay, so in practice in Alice, this is done with using different devices. So in order to avoid autocorrelation of particles, so you can't measure V2 and determine Q2 in the same momentum space or in the same rapidity range. So what we do, we can, for instance, measure Q2 and select Q2 in the so-called V0C detector, which is on, I always forget, C is, anyway, the V0 are scintillator detectors that measure the multiplicity in the forward direction. And so there's a V0A and a V0C. And so we can measure Q2 in one of those, and then we're going to measure the flow of the particle in the central detector. We can do this in centrality classes, and so here I have central to mid-central. And what's shown is the V2 that we measure in not only centrality classes, but Q2 classes. And so here, Q2 is as a magnitude, I select the bottom 10% or the top 10%. And by doing so, I'm transforming, or I'm selecting the shape of the system. And so here, the bottom 10%, I have small V2. The top 10%, I have large V2. And you see this repeatedly in each of the collision centralities. This is very instrumental in the search for the CME effect, trying to understand what is the background of the CME and whether there is any CME for that matter, but I'm not going to talk about that. We did a lot of studies to see how indeed this event engineering can be measured explicitly, and how it influences the V2 of particles. And so this is the V2 with the reaction, the event plane method measured as a function of momentum. And the black points are no selection. The red points are the top Q2 range. The blue point, the bottom 10% Q2 range. So you see that by selecting larger Q2, you indeed increase the V2 that is selected. So it's, I mean, in some sense, it's built in. You make it this way. What's interesting, though, that when you do this, you can take a ratio of the top to bottom selection, and you can take these ratios as a function of momentum, and these ratios are shown here. So you find that the ratios are actually independent of momentum, which means that the geometry is essentially also independent of momentum, which is what it should be if it's really geometry. It's even more interesting when you look at D mesons and J psi. I have a slide for J psi, but I'm not going to discuss it. But let's discuss the D meson. Are the D meson flowing? And is the flow of the D meson connected in any way to the rest of the system? And so again here, the black points represent, obviously D are rare. D mesons are rare. They're hard to measure. But the black points are the flow of the D mesons without selection. The red points, again, are the top a class of Q2, so you have deformed the system, you're looking at deformed system, and you see that when you have such a deformed system, the V2 of the D meson is larger, and when you look at less deformed system, the blue points, you see that the D mesons have smaller V2. And so what this tells you is that the D mesons are actually coupled to the system. The D mesons are not independent of the system, they're flowing through the system, they collide with the system, they interact, and there's some level of dissipation, and therefore there's some level of coupling. Understanding that coupling will be very interesting. Same thing was seen with the J-psi, but I'm not going to discuss it. If I have a little bit of time left, I will talk about one more result, which, again, another idea, brilliant idea by my colleague Voloshin, and a student that completed his PhD with him. The idea was to measure HBT with event engineering. And so HBT, as you know, involves the measurement of a two-particle correlator for identical particles, and the correlator has this shape and this expression. And so in this particular analysis, you can break down the correlator in terms of the outward momentum of the pair, the side momentum of the pair, and the long momentum of the pair. So you can analyze the shape of the system along these three axes. We know already with HBT that there is a momentum space correlation. So if you have expansion of the system, because the system, if your detector is here and you're looking at pair in this direction, if the system is expanding this way, you will have a narrowing of the correlation with momentum. But now the idea is to not only do HBT, but to engineer the events, that is to select the events on the basis of their deformation, their V2, and see what we get. So just to emphasize this, by measuring Q2, I can select how elliptical or elongated this event is. And my interest is to look after the system has evolved and eventually freezes out, and then I can measure HBT. HBT is determined by the last interaction point of the pions, so HBT tells me the shape of the fireball at the very end of the evolution, and the amount of V2 that I have in the system tells me the shape at the beginning of the system, evolution of the system. And so I can then look at how V2 is influencing the final shape. And so that's the idea. So first you can do three-dimensional analysis of the radii, the system radii. And so there's no engineering yet in this case. So this is the radius out. This is the radius side, and you can see that there is, for different momentum ranges of the pair, you can see that there's an anisotropy, so there's a modulation. And so when you look in this direction, the particles are flowing faster, so at 0 degree, you will see a smaller width of the system. When the system is side this way, you will see a larger system. And so here, our out is small, our side is large. When you're looking at 90 degrees, you expect to see, in this direction, the side direction, you expect to see a smaller system, and that's what you see. Whereas in this direction, the out direction, you expect to see a thicker system, and that's what you see. So we understand the geometry, and now we can try to understand how it behaves as a function of the initial eccentricity. So this is the final eccentricity of the system measured with HBT, and this is the initial eccentricity based on the V. And then you can see there's a linear relationship between the initial and the final eccentricity of the system. The punchline is that, well, there's a correlation, and we were thinking that perhaps the expansion of the system would be so violent that you would go from this shape to that shape. In other words, that the shape would become very elongated along the reaction plane. What we find is that equal eccentricity line is here, and so the final eccentricity is always below the line. It means that the system after expansion is still a smaller radius or smaller dimension along the reaction plane. It has expanded, but it's still smaller along that direction. Now, this has also been done with event engineering, and so by selecting on Q2, you can increase the V2 that you get. It's a very small effect. So, and I will end on this. So you have a very, very small effect here. Bottom Q2, higher range of Q2, and you can see that by changing Q2, you can actually change how the system is expanding. So it's a really, I think, it's a beautiful measurement. On the one hand, it's also a fantastic challenge for the theoretical community to try to see if they can describe the hydrorevolution to the extent that they can reproduce this result. So in summary, I think I've tried to show you an array of results that convince us that we have a thermalized system where there's saturation of strangeness, where there's very high temperature, equal number of particles and antiparticles, that with this huge expansion radially or transversely, and that we're now along the way, very well along the way to understand at the very least the shear viscosity of the system, if not other properties. Certainly the heterochemistry of the system is already very well understood because we know that we can reproduce the ratio of particle abundances with a thermal model quite well. And so there's a lot to be done, of course, understanding the small systems, but I think we've already achieved quite a bit in the first 10 years of the machine. All right, I'm going to stop here.